All right, so welcome back. Yesterday, or last video, we talked about taking a statistical point of view when we were measuring something. We had a value, we were measuring the same thing multiple times, and we found, no surprise, that we got a slightly different answer every time. That's due to uncertainty. And we could define some quantities, like the mean and the standard deviation of the mean, to find out what our best estimate of that value is that we were measuring, as well as our estimate of its uncertainty and the uncertainty in our value. Those are the mean, the standard deviation, and the standard deviation of the mean, respectively. And today we're going to continue that. We're going to take it a step further. And we're going to look at measurement itself as, instead of taking out a ruler and measuring the true value, we're going to look at all measurement as sort of sampling from a underlying probability distribution associated with that measurement system. So if I'm measuring the length of something, I'm actually going to be looking at this as sampling from a random distribution, a particular distribution, and we're going to get into that today. So to start, let's just recap where we were yesterday, and we're going to rearrange the data to take a different viewpoint. So let's look at our K measurement. I'll pull it up here. Okay, and that's what we had. So let's calculate the mean again. Let's just write down what the mean is, and we're going to rewrite it slightly differently. Okay, and that was our basic definition. Let's write it explicitly. And this is what we had. Before we compute the sum, let's have a look at this. There are certain values that appear multiple times. For example, we had 4 appearing 3 times. We had 7 appearing once. 5 appeared twice. And 6 appeared once. So let's write this in a way that might seem initially contrived, but you'll see where we're going with this very quickly. So we can write this mean as follows. So we've just carried that 1 inside. So in general, we can write this like this. If there's n occurrences of a given number, we can write our definition of our mean as follows. Okay, it's really the same thing. We've just rearranged it. Now, what is this term? What is this green term here? If we look at it, it's the number of times out of the total number of times that it appeared. This is actually telling us the chance that something appears. In fact, if we take the limit for very, very large n, what we actually get is the probability. So this becomes the probability of measuring Ki. And this becomes a more and more accurate description of the probability for larger and larger sample numbers. Measure 100 times, we get 67 times we found 5, for example. The probability is roughly 67% that we're going to find 5 on the next time we do a measurement. So let's rewrite this. We'll continue rewriting it like this. So the mean value of K is the sum of K times the probability of that particular K for all K. And this is the same formula as before, but we're actually just writing it slightly differently. Note that necessarily, if we just sum up not the mean value of K, if we sum up just the probabilities, we're going to get the sum of all the individual occurrences divided by n, the total number of times we measured. That's always just going to give us 1. Okay? So this is a way of looking at the average value. We can rewrite it this way. Similarly, we can do other things. We won't get into it too much with the discrete sums here, but we can write the standard deviation this way. For example, let's just write the standard deviation squared this way, or the standard deviation itself is just a square root of that. So we can generalize this process to averaging over other things. And what we're doing is we're weighting the average as a weighted sum of the quantity in question. Okay, so this is great. This actually tells us something. This actually brings us somewhere useful. So we can now do something called making a histogram. And what we're going to do here is we're just going to plot the number of times each value occurred. So here's K, and on the y-axis it's the number of occurrences of K, which we're just loosely writing as probability of K. So what does it look like here? We had 0 for 3. We had 3 for 4. 5 happened once. 6 happened once. And 7 happened once. And that's the histogram of our measurements here. Now let's see what happens as we take larger and larger numbers. So what we're going to do is just simulate some data. I don't even have any springs on me or little masses, so we can't do this experiment, and I'd rather not do this 100,000 times like we're about to do. So let's move over to our Jupyter notebook. I'm Here's our notebook from last time. So what I'm going to do is, let's just say we're measuring something, a position. Let's say we know the true value is 57 millimeters or something like that. And our uncertainty that we've inferred somehow, our underlying uncertainty, is, I don't know, 2.5, just for example. Okay? So let's actually look at this. Let's see what we'd get if we plotted a bunch of things, if we made a bunch of things. I'm going to do some Python here. How many measurements do you want to take? Well, let's take initially 10 measurements. And what I've done here in a line or two of code is just simulate this. And let's plot what we get. So we're just going to plot, we should say we're measuring. We're plotting x, or measured x. And we'll give it data points. Okay, that was our measurement. And if we took a bunch of different measurements, let's say we took 100 of them, our measurements would look like this. If we took 1,000 measurements, we'd start to get something that would look like this. Okay, so either way, we're going to measure this. And let's look at the histogram of this particular data. So I'm going to go histogram of x, and bear with me, this is what we get. Not super exciting. We might get a different set of values every time, but this is the sort of pattern that emerges. We can tell how many bins we want it to put into. So here we have a bit of a trick. We might be getting values that are not integers, but each bin instead of just being 55, it looks like this is any value between 55 and 55.5 in this case. We'll go here. There's nothing that happened in between, and similarly for 57 and 58. So it's just, if it's between 2 points, we're going to bin them. That's how a histogram works. So let's say n bins is equal to 10. I want to make 10 bins. Oops, bins. It just turns out I don't know how to program in Python. It's called bins, not n bins. Okay, and that's our histogram. Not very telling. So let's crank up the number of measurements. Let's go to 100 measurements, and we'll see what we get. Okay, starting to look like something. 1,000 measurements. It's really starting to look like something. 10,000 measurements. We can see a shape emerging. Now, they've only have 10 bins here, so let's actually make a few more bins. 100 bins here, and we can see that here's our measurements. It's really starting to take a shape. Let's add another, this is a nice thing about simulation. We can just keep adding virtual measurements. And look at this. We get this distribution arising here. So what we're actually seeing here is if we take enough measurements, we actually can visualize the underlying probability distribution associated with our measurement. So let's think about what we're actually doing here analytically. So I'm going to insert that plot. And that was our histogram that we got from our virtual 100,000 measurements. And we can notice that there's a shape going on here. There's like an underlying curve, and I'll do my best to trace it, that is somehow a continuous, looks like a continuous function. So the one thing that we can note here is that what we actually did there is take a continuous variable. We were pretending we were measuring position, which is not discrete, but can take a continuum of values. So let's extend our analysis from before to handle continuous variables. Okay, so before we had this, and now we're going to go to a continuous variable. And what that means is the spacing between the sum is going to become infinitesimally small. This is the definition of, or a definition of the integral. So we're just going to replace that sum with an integral, and it's going to look like this. Okay, it's really the same thing. So a few notes here. So first of all, by convention, we're going to go from minus infinity to infinity. We're going to consider all possible values. If those values are not possible, well, in those cases, the probability is 0, and it doesn't add anything. We don't lose anything from including it. So it just makes a clean integral. Okay? The other thing is, what is PR of x? That's what we call the probability density function. So the first thing to note is that if I integrate the probability over all possible values, the probability that something happens is 100%. Okay? So I'm going to get some value, I don't know what it is, but the probability that we're going to get anything, so we integrate over the entire probability distribution, is 100%. And what that hints at is that I can ask, what is the probability, so here we are, what is the probability of getting 60? What's my probability of getting 60 here? Well, this is where it becomes subtle. So what do you mean 60? Do you mean 60? Do you mean 60.00000000? 1? Or is that different from 60.0000000, right? The probability that x is equal to 60 exactly is 0. There's no way you can specify. You need infinite precision. And there's always infinitely many points that are in any neighborhood around 60 here. So the probability of a particular value in a continuous distribution is 0, always. But what does make sense is we can ask, what is a probability that x is between 59.9 and 60.1? Or we'll just say x is between 60 minus delta and 60 plus delta, for example, or between x1 and x2. That is a non-zero quantity, and we get that just by integrating the probability distribution. It'll just be that. It's an area. The area here is the actual probability. Green is a poor choice for color here. There we are. So that area gives us the probability. Okay, so that's an important point. That's why it's a probability density function. Just like we had a mass density, we integrate it to get the mass. Probability density function, we integrate it to get the probability. Okay, so it tells us how to get the probability. So the probability of finding a value between 2 points is given by this integral here. And we can do other things as well. We can talk about the average value of, for example, x squared. And that's just given by the same prescription. Or the probability of x minus x naught all squared, which is our standard deviation. And we can do this for any function. So the average value of f of x, given that probability distribution, is just going to be the integral of that function weighted by that probability distribution. Okay? We might use this once or twice, so it's a good thing to know. Most importantly, we want to know the mean from here, and occasionally we want to know the standard deviation directly. And this is a probability distribution. Okay. The next thing we want to talk about today is a particular probability distribution. The most important one, and we'll talk about why it's the most important one soon, but a particular probability distribution called the normal distribution or the Gaussian distribution. So this is a plot of what the normal distribution looks like. It's the classic bell-shaped curve that you see all over the place. Okay? So let's write down the functional form of this. So it's a probability distribution, probability density function. And let's write this, this down. And basically what it is a negative exponential of a square. So this term in the exponential is always positive. So it's the same positive and negative, and that's why you can see that it is symmetric about x naught here. So that's good. And then it has a bunch of other squiggles here, and they're there for a reason. So first of all, it has this term here, this 1 over square root of 2 pi times sigma. That's for normalization, or a fancy word, meaning that if I sum up or integrate out all the probabilities, this ensures that the integral is equal to 1. The probability of getting some value is always 100%. That's all that does. We're actually going to show that very shortly. The next thing to note is there's these other terms in here. What is this x naught? Well, here, x naught, as it turns out, and you'll have the pleasure of doing this on your assignment, x naught is equal to the mean of the function described as above. And this will be something you do not have to do, but we may do later as an in-class example. Sigma is the standard deviation. So this has all the, if we had data which was described by this, the mean of that data would be x naught, the standard deviation would be sigma, and it would be a valid probability distribution. Okay, so on this plot, let's just plug in a few things. So what is the maximum value that this takes, by the way? The maximum probability is when x is equal to x naught, and that's going to be 1 over square root of 2 pi times sigma. Okay. How about for other values? Well, at some point, it's going to fall to 1 over e. 1 over e is this famous number that we always talk about. We had it for capacitors. It was that characteristic time scale. There's a characteristic deviation from the mean in this as well. So let's just think about that for a sec. When x minus x naught is equal to sigma, that's a characteristic distance, then our term goes to our probability, density falls by this much. We have our max value, that's just what we had before, and this x minus x naught is sigma, so it goes as e to the minus sigma over root 2, so it's 1/2. Okay, so this e to the minus 1/2, whatever this value is, it turns out we can do it numerically. It's about 60 some odd percent. Let's actually, we have Python open, we have a Jupyter Notebook open, so let's figure that out. 61%, okay, good to know. 60.6%. Okay, and that gives us the width. So about just over halfway up here, the deviation is 1 sigma, and we're -1 sigma on the other side here. That's when it falls to about 60% of its max value. Here on this plot, x naught is just the mean. Okay, so let's think about this. The smaller sigma, the smaller our uncertainty, the tighter that distribution is. We have a more sharply defined distribution, and this makes sense, right? For our measurements, we're not going to have so much variation about the mean. If we have a large sigma, large standard deviation, we'll have a very wide set of fluctuations about our mean. Now, this is such an important distribution that it helps to be a little bit well versed in how to deal with it mathematically. So let's do a simple calculation. Let's prove that this thing is normalized. And then we will modify this integral. We can modify this integral slightly in order to do the calculation of the mean. And then I'll show you roughly how to do that, but that will be one of your final assignment problems. So let's actually integrate this. So let's look at how you integrate this beast. All right, let's roll up our sleeves and we'll get to it. All right, terrifying. So let's figure out how to deal with it. Well, the first thing we're going to do is let's just do a simpler case. It's always a good idea to do a simpler case too. And it turns out that this version of the simpler case is going to make our next step very easy. But if you ever see something like this and you just don't know where to start, try to make it as simple as possible first. So let's first just integrate this. Okay, so we've gotten rid of all those crazy constants. It's still formidable, but there's a few ways of doing it. We'll call that value something. So here's a trick. And if you haven't seen this before, it is a trick. But once you've seen it a few times, you kind of get the hang of the feeling for how to solve these sorts of integrals. So what we're going to do is we're going to call this integral I. Okay, I. What is I? I is a Gaussian, and we want to integrate it. We want to find the area under it. And in order to do so, let's actually consider I squared. Let's write that down. It's this integral squared. So we're going to have two integrals here. Now we can't use the same variable, I guess. So we'll use another one, w, for the second one. Okay, and we're actually just integrating. Let's draw this now. What are we actually integrating? We're integrating something along the other dimension here. So the square of it, what we're integrating a surface like this. That's what this function of two variables looks like that we're actually integrating. So let's rewrite this. And what are our coordinates here? Well, we have w and z. And notice that this integral, when we look at it, it's rotationally symmetric. Okay, so we can integrate along. If we find it for one angle, it's the same for all angles. And this sort of thing screams polar coordinates. So we're going to use polar coordinates. We're going to let w and z be our x and y, so that w squared plus z squared is equal to r squared. Okay? And there's no theta dependence here because it's the same for every angle. And when we do that, we have to write dw by dz is equal to r, that's our dr rather. That's how much we're moving radially and how much we're moving orthogonal to that. And the arc length is s is equal to r theta, so it's r d theta. R dr d theta. Okay, so let's continue writing this simplification. Believe me, it is a simplification. So I squared is equal to, we're going to go from theta is equal to 0 to 2 pi, all angles. And what should we include for r? Well, we're going from 0 radius all the way out to infinity of this integral here. So we're going to get r from our r dr d theta times e to the minus r squared dr d theta. Okay? Since there's no theta dependence, let's just pull that theta out of there. Now, even a simpleton like me can integrate this one. So we're going from 0 to 2 pi of a constant. That's just 2 pi. All right. So we have 2 pi times this less trivial integral here from 0 to infinity of e to the r, r times e to the minus r squared. But this is something that is very conducive to substitution. For if we let u equal r squared, du is equal to 2r dr, right? So r dr is equal to 1/2 du. So this is going to give us what? I squared is going to give us 1/2 times 2 theta, times 2 pi, and we get e to the minus u du. Now it's looking easier. So if r is equal to 0, u is equal to 0. If r is equal to infinity, u is equal to very infinity, but it's still infinity. So it's going to look like this. And this integral is not actually so bad. This integral right here is just minus e to the minus u evaluated from 0 and infinity. And that's going to give us minus 0 minus 1. That whole thing is just equal to 1. Beautiful. So this whole thing is just equal to 1, and therefore my integral is equal to pi. What isn't equal to pi? All right, so I is equal to root pi. So we just found something. We found that the integral is equal to, what do we call it? We call it e to the integral, of this e to the minus z squared, dz, is equal to the square root of pi. Man, we've done all this work and we haven't even gotten to the main event yet. We haven't even gotten to integrating what we wanted to integrate, which was this fella. But we're actually already pretty much there. Because now we can do a change of variables. So let's bring this down, okay? And we're going to do a change of variables. Now let's let z equal x minus x naught over the square root of 2 times sigma, so that dz is equal to 1 over the square root of 2 sigma times dx. Okay? So dx is equal to root 2 times sigma times dz. So we got this. I've separated those things out just to make it easier. And we're going to integrate what? We're going to integrate e to the minus z squared. It looks like we pretty much know how to do that. Now, we have to be careful here. If x goes to infinity, okay, good, z goes to infinity. If x goes to minus infinity, z still goes to infinity. So our bounds of integration are still from minus infinity to infinity. And look at this. We already know how to do this one. So first of all, these, So first of all, these sigmas and root 2's will cancel. And this is 1 over the square root of pi times this integral, which we just found out from above, is equal to the square root of pi. So we got a cancellation, and this integral is 1, okay? A lot of math, not a lot of experimental physics, but it's important to know how to do some gymnastics with these Gaussian integrals. They come up a lot, and we'll need them to calculate the mean. And we're really going to need them for the next thing, which is going to be tomorrow's lecture, the live lecture, where we're going to answer the following question. We're going to ask, given my model, given my theoretical model, which predicts that my variable is a Gaussian with a given standard deviation, say it's a Gaussian centered at 57 with a standard deviation of 2, say I measure 72, what is the probability that that actually happened? And this is very important because this is the heart of experimental physics. Is my model wrong, or is my measurement consistent with the model? So we're going to talk about the subjective whether or not your measurements are consistent with a statistical model or a physical model, or whether or not you have a large violation of that model. If you do, maybe your measurement is wrong, so you'd be very careful about your measurement. Once you've ruled out all those possibilities, you have to conclude that there's something else going on physically in your model. And that is typically spoken of as like an n sigma deviation. So a 5 sigma deviation means if the sigma is here, we measured something right here, and we did it very carefully. And this probably means that there's something going on. It also could mean that there's something wrong with your apparatus, and that happens. So it'll justify us when we say, I'm not going to throw out this data point, but I'm letting you all know about it. Okay, and that's going to be tomorrow. So this is a very mathematical one, but thanks for bearing with me, and we get to use it next time.